Okay, class, chapter 4. This is exciting. We're almost done a whole journal. So in chapter 4, chapters 1, 2, 3, we're doing lots of derivatives, right? That's a big part of calculus, but what's the other half? Integrals. So we're finally ready for that in chapter 4. And start with using integrals. So think about what was the main use of integrals back when you're doing Calc 1 area, right? So if you had to take a guess, now that we're kind of expanding in dimensions, what do you think the main use of integrals in Calc 3 is? Volume, right? So we're going to start by talking about approximate volume and exact volume. And just like we did with area, you talk about approximate area first. You built that up with what? Do you remember what those were? The technique that you used was called? Okay, that was a Riemann sum. We're going to do the same thing, but it's going to be in higher dimensions. So back in R2, we talked about area, and we did it two ways, approximate. And the pictures would look like this. You had some function. You were interested from A to B, what is this area? And you would do it by dividing this into some little rectangles. You usually try to make them have equal width. It's not necessary. That's still a Riemann sum, even though that one's skinnier. But it's a lot easier for the formula if they all equal width. That makes a Riemann sum. We're going to do the same idea, just in higher dimensions. And then eventually you got to exact area. And that same thing, y is a function of x, from A to B, you could now get this shaded region exactly, and you did that with an integral from A to B, f of x dx. It was really neat that that was just a limit of the Riemann sums as the number of rectangles went to infinity. Okay, well, we're going to do something very similar. I'm going to start with a visual aid. So this is my dog's like little hole. She goes in a little sleeping bag, so she can go in there. Imagine it actually stands up a little bit better. It's older, so it just wants to collapse. But imagine it's an R3 surface over the top, right? And so something that approximates that decently well in R3 now is z is a function of x and y. And let's say it's the square root of xy. Okay, and let's just take a look and see how close that approximation is with the tech tool. In my head, I think it should do a decent approximation, but let's see. So we'll share the screen. Oops. Let me try this again, share the screen. And let's take a look at, in CalPlot 3D, let's plot. Okay, here's our surface. Again, it helps, it's a little harder to use the mouse to control. It's better if you use the arrows. And let's take a look. Okay, that's not too bad for her. Hers kind of comes, Chiche's little sleeping bag has a bit of rectangle, but it has the hole maybe over this area. So that'll work. That'll work for us to do this as an approximation. Okay, stop share. Okay, so again, we're going to use this surface to approximate Chiche's sleeping bag here. And we're going to talk about what we really want to do is get the volume inside of this, right? So here's a surface over some region in the XY plane, that's the bottom here. And we want to get the volume of, you know, how big of a dog can I put in here? So I should show you though. Chiche's little. She's a little Mexican hairless, but I could probably get a medium dog in there. Okay. All right, so we're going to try to approximate. We want to approximate the volume of this function, but we have to do it over a region. And so let's just to keep the math easy, we'll say x is between 0 and 1. And that was the picture I just showed on the screen share. I limited the x and y range. Okay, so in the XY plane, we have this region. And we're always going to call these regions R. So here's our region, and then there's this surface over top of that when the z-axis comes out from the board that comes up something like this. Okay, and so the idea with approximate volume, the very first methods for doing this was, if you read Novella 3, Kepler, who was the Kepler planetary laws of planetary motion. Same guy, he was also really interested in math. And the little historical tangent is, he was getting married, and the guy selling the wine for the party, the wedding party, came in and put down a bunch of wine barrels, and all the barrels were different sizes, but he was just charging him like by the barrel. And so this didn't seem fair to Kepler. And so he thought about, is there a better way to do this accounting? And he ended up writing a whole book about it, and basically how to get volumes of wine barrels. And because every barrel is slightly different in height and width and, you know, girth, I guess. And so he made this method, and his method ended up being sort of the precursor to what we're going to do with Riemann sums. And his idea was, I'm just going to shove a bunch of shapes inside this barrel, and shapes that are volumes that I know how to compute easily. So we're going to do this, pretend we're going to do this with Chiche's sleeping bag here. So just to visually, she's trying to get in here, I got to get her out of it. I'll let you have it back in a minute, Chiche. So you take something like this, like in the way back, I need something small. So I'll take a little can. Easy to get the volume of this, right? This is, the cross sections are all circles with pi r squared times the height. So I'm going to take that, and I'll shove it way in the back. And if I had a bunch of those, I'd shove those little cans way in the back, and I count how many I put in there. And then maybe I've got some other ones here. These are different radius, different height, but I could still get the volume of the cylinder and put those in, right? And I just keep on shoving. Got a really big one here. What is this? Tomatoes. Lots of tomatoes there. So a really big one, same thing, pi r squared times h. That would go more towards the middle or the front here. And so I just keep shoving shapes whose volumes are really easy to compute. And so once we've done that, we filled it up completely. We would take out all the cans that we had, let's count them, get the volume of each one, sum it up, and we'd have our approximate volume. One way to do it. But if you're thinking about shoving cans, what I would be doing over here in this picture is I'd be shoving, let me stand over here, like I put the little can in the back, and then I had a bigger, like that bigger tomato one. But what's the problem with putting circular things in there? Yeah, the cylinders are easy to get volumes of, but they're not filling the space completely, right? That's a whole nother really neat math problem. Take some of my graduate classes. The knapsack problem and the bin packing problem. You want to pack as many things in there as tightly as you can, given certain constraints. Well, we can easily see that circles aren't going to do as good a job as what? Rectangles, right? So, and that's the same thing over here, right? It makes sense to use rectangular things, not just because they're really easy, but because they can jam tighter to each other, closer together. All right, so in this one then, maybe I should come in, and the easiest thing might be to just turn them into squares, right? Just 4 squares. And then those would be the bases. I'd have these rectangular prisms then, right? I'd be jamming things that look like this, square bases, but different heights, right? I might have ones in the back that were smaller. I jam those in, and then I have some more in front, and so on. And jam each of those in. Well, what is the volume of those? Length times width times height. No problem. And you can easily figure out the area of the base times the height. So the area of the base in this particular example, no problem, right? This is a half right here. This is a half. So the area of each of these squares is a half times a half is a quarter. And then to get the volume of each one of these rectangular prisms, I just have to figure out the height. Now, how am I going to do that? How am I going to get the height of each of these? Well, again, think about what's actually happening is there is Chiche's sleeping bag surface lives over top of this. And so I want to go from the XY plane to the surface. And so I want to get my height. And I have to figure out, there's many ways I could do it. Just like over here. How do you decide the heights of these rectangles? You had left rule, right rule, mid rule, Simpson's rule, track rule, so many rules, right? But you've usually just focused on the left, right, mid. We're gonna do something similar over here. What are some choices for figuring out the height of each of these rectangular prisms that are coming out and going up to the sleeping bag surface? So I could do something like this. I could try taking these 4 points and then going up to the surface there, and those would be my heights. So this is what is called the lower left, because in each of the boxes, which happen to be squares for us, but in general it could be rectangular boxes, each one of those, I choose the lower left point, and I'll evaluate the function at that point, and that'll be my height. So we're going to do this with Riemann sums. We're going to be adding up the height of 4 boxes. So let's see. This one is at the point 0, 0. So I need to figure out what f of 0, 0 is. Plugging into my function, 0. The next one, this is the point 1/2, 0. So I'm going to plug in that. I'll get 0, 1/2, oh sorry, 0, 1/2, and 1/2, 1/2. In this case, this is called an n equals 4 approximation because I used 4 rectangular prisms. So I need to go ahead and compute these. And this will be 1/4 square root of 1/4, which is 1/2. Okay, so it turns out the only one that actually makes a rectangle for the lower left is the last one. This one over here actually comes up from the XY plane, comes out of it. These other ones are flat on the board here. So not a very good visualization. This is the only one that has any height. And it is 1/2 by 1/2 by 1/2. So the volume of that one is 1/8. Plus a volume of 0, plus a volume of 0, plus a volume of 0. So our approximation for the volume is that it is approximately 0 plus 0 plus 0 plus 1/8. So probably not a very good approximation. Let's try another one. So that was the lower left, but we could come over here and instead of doing lower left ones, let's try one that generally does better, just like it did over here, was the mid. So let's try the mid rule. So these points now still the area of each rectangle is 1/2 times 1/2, which is 1/4. And then we just need to get our heights. So the only thing that's going to change from the lower left rule to the mid rule is the heights. N equals 4 mid rule. I will be getting f of, that's 1/2, that's 1, so that would be 1/4, 1/4. And that's the square root of 1/4 times 1/4 is 1/16. The square root of that is 1/4. Okay, so the first box has the area of 1/4 times the height of 1/4. So the volume for the first box is 1/4 times 1/4 times 1/4. So 1/64. Okay, a couple of you noticed what I just did in the example, that I made a mistake in my calculation, that I wrote the volume of that first rectangular prism was 1/4 times 1/4 times the height. And of course, the area of this little square is 1/2 times 1/2. So it should have been, and what will be in the next few minutes, I should keep saying 1/2 times 1/2. So when you see that 1/4 times 1/4, just know the picture is 1/2 times 1/2 because you're getting the area of the base of the rectangular prism, and you're going to multiply that times the height of the rectangular prism, which is just given by evaluating the function. So I got too many quarters in there, so all of those quarters there. Okay, so in the next few minutes, just You'll see that arrow pop up a few more times, but the idea is the same. Get the area of the base times the height of the rectangular prism. And thanks for the folks finding that for us and correcting the error. So hopefully the last few minutes of this video, that clears things up. Again, there's a little rectangular box above that. Let's do the next one. Let's look at this box. This is at x equals 3/4, y equals 1/4. We want to figure out how far out from the board have we come until we've reached the surface, the square root of x times y. And so that'll be, let's see, 3/16, the square root of 3/16, which is the square root of 3/4. So then our volume for that rectangular prism, the one sitting right here coming out from the board, would be length times width times height, which is 1/4 times 1/4 times the square root of 3/4. So that's the square root of 3/64. Okay, 2 more rectangular prisms to do with the mid rule. Let's do this upper one here. That is when x is 1/4, y is 3/4. Plugging that into the function gives me the height of this rectangular prism. So that'll be square root of 3/4. The volume then of the one that lives right here, this rectangular prism that lives over this box in the xy plane but goes up to the function, up to the surface, will be length times width times height. So we'll get square root of 3/64. Okay, one more to do. All the way over here. That's the point f of 3/4. That evaluates to 3/4 times 3/4 and the square root, so we'll have 3/4. That is the height of that final rectangular prism. The volume then is 1/4 times 1/4 times 3/4, which is 3/64. Add all that together, and we'd say our approximate volume over this region, under this surface, for the volume of approximating Chi-Chi's sleeping bag, the volume of Chi-Chi's sleeping bag, we'll be adding all this up. So let's see, we'll have 4/64 plus 2 square root of 3/64. So whatever that decimal is, that's our approximation. And then you can also visualize this with a tool to see whether or not you think, just like you did over here, overestimate or underestimate. And if you've drawn a good picture and a good surface, it's very easy to see overestimate or underestimate. Okay, so let's summarize a couple of the points. We're going to approximate volumes using rectangular prisms because they jam together tightly in any space. The heights of those prisms can be evaluated many different ways. We showed with the lower left and mid, but you could do, say, upper left, upper right. There's all sorts of other, just like the Simpson's rule is a nonlinear approximation. But the main point is no matter which of these you use, like this one we knew was going to be a gross underestimate, right? It's pretty easy to see that because those other several of those rectangular prisms didn't even exist. They stayed flat on the XY plane. Gross underestimate. I'm not sure how good this is, but we know mid's usually better than the lower left, than all the lefts or rights. So for your work, even though we had to do maybe more fractional work, this is usually better bang for your buck for the amount of computation. But the key thing is, what happens if we just make more and more ends, which is another way of saying like making the area of each of those smaller. So you can either let the change in the area, dA, go to 0, or you can let n, the number of rectangles that you're using, go to infinity. Same thing we did over here. What happened back in R2? In the limit, as n goes to infinity, this approaches then an exact volume. So we'll see that. We can make our approximation as good as we want if we just have enough time to do the computation or program a computer to do it. All right, so let me make sure I've commented everything I want on this example. Okay, All right, so that's this video. The next one we'll do tech tools that help us make this end get bigger and bigger. The video after that will be exact volume, and then some tech tools for exact volume.